it's my great pleasure to introduce our distinguished lecture series speaker, which is going to be Professor Hugh Woodin. Let me give a brief introduction. He's a professor at the Department of Mathematics and Philosophy at Harvard University. And he's also a distinguished emeritus professor at University of California, Berkeley. Hugh got his PhD in '84 at UC Berkeley under the supervision of Robert Solovay. And since then, he's become a leading set theorist. His work includes contribution to the theory of inner models, determinacy, functional analysis, recursion theory, large cardinals, and a very famous large cardinal, the so-called Woodin cardinal, bears his name. Hugh has had many honors, just to highlight a couple of them. In 1989, he received the Carol Carr Prize from the Association of Symbolic Logic. He was also a plenary speaker at the International Congress of Mathematicians in 2010. And he's also a managing editor of the Journal of Mathematical Logic. Today, he's going to be talking about infinite necessity.
Well, thank you all for coming. This is actually the first lecture I've given since the before time without a mask. So it's going to be a new experience for me. I was looking at the clock and I realized this almost became a very long lecture because that clock is not running. That would have been a different form of infinity. See if this works. Okay. Maybe it doesn't. Oh. Okay, so I'm going to start with number theory. So we have the natural numbers, 1, 2, 3, and so forth. Or as a set theorist, I view them as 0, 1, 2, and so forth. Oops. They're the formal axioms of number theory, the piano axioms. They include the algebra axioms, the axioms you would write down, and the induction axiom, which basically says if you can define a non-empty set of numbers, it has a least element. And the question is all of mathematics just the study of the formal consequences of PA? If it is, there's no infinity. Okay, well, we can move a little bit beyond that and go to second-order number theory, formal second-order number theory. So now the objects are the natural numbers together with all sets of natural numbers. And we have similar axioms. We have the algebra axioms of number theory. We have the induction axiom, which is now just a single axiom. It just says that every set of numbers, which is non-empty, contains the least element. And then we have the comprehension axioms, which say that if you can define a set with a formal property, it exists. I'm not going to specify any of the axioms any more than that. So we have two fundamental structures of mathematics, the structures of number theory and the structure of second-order number theory. Okay, so probably one of the most famous modern theorems is Wiles' theorem, Fermat's last theorem. If you have a natural number bigger than 2, then for all natural numbers x, y, and z, x to the n plus y to the n doesn't equal z to the n. Okay, that was proved 20 years ago-ish. Now, ZFC are the formal axioms for V, the universe of sets, and V is the ultimate generalization of the natural numbers. Curiously, the published proof of Wiles is not even in ZFC, and it's certainly far from a proof in second-order number theory. It uses infinitary methods. And so a much discussed problem is, can Wiles' theorem be proved in number theory? But I'm going to make the claim that's not the right question. So what is the right question? Well, let's talk about finite number theory. So in finite number theory, we have the objects are the numbers starting with 1 up to some unspecified largest number. So we have the formal axioms of finite number theory. We have the algebra axioms, but addition's not total, and multiplication's not total. So you just write the obvious variant. They're relations. When does x plus y equal z, and so forth. This is not addition and multiplication mod n. I literally mean we restrict the integers to 1 up to n. Plus and times are partial operations. What about the induction axiom? Well, there are many different ways you might do it, but this seems to be the most interesting one. It's the pigeonhole principle, and it's not known if it's equivalent to how you would usually formulate induction. So this just says that if you have a function on numbers and f is defined by a formal property, then it's 1-to-1 if and only if it's onto. You know, if you think about it, that makes sense, right? So that's going to be the induction axiom. All right, what can you do? Okay, so for every natural number n, if we look at the numbers 1 up to n, that's a model of finite number theory, finite FPA, not FPA. 1's the simplest model. And then you have the model which has just 1 and 2. And then the model with just 1, 2, and 3, and so forth. So it's fun to play around in this theory. And if you do that, you realize you can define the relation z is equal to x to the y as a partial relation in finite arithmetic. It's a trick where you break down the exponents. So Fermat's last theorem is a formal statement in FPA, in finite arithmetic. So can you prove it in finite arithmetic? If the answer is yes, then mathematical infinity plays absolutely no role in Weyl's proof. There is no room to use infinitary methods. You can't even do asymptotic methods in finite arithmetic. You're going to have to do nitty-gritty fine estimates. The Riemann hypothesis can be reformulated in finite arithmetic. In fact, most of the famous open problems of number theory can be refined to problems in finite arithmetic. Usually it's a sharper form where you've actually made some explicit estimate. Like if you take the ABC conjecture, which has been much in the news, that looks far from a universal statement in arithmetic. And yet there's a refinement of it due to Baker that makes perfect sense in finite arithmetic. So is all of mathematics really just the formal consequences of finite arithmetic? No infinity at all. Well, let's look at a simple example. Euclid's theorem that there are infinitely many prime numbers makes no sense in finite arithmetic. But Bertrand's postulate does. So Bertrand's postulate is the statement that for every number n bigger than or equal to 1, there's a prime number in the interval from n to 2n. That makes perfect sense. Clearly a stronger theorem than saying there are infinitely many prime numbers. Now, the best proof of Bertrand's postulate is due to Erdős, the so-called book proof. And if you look at that proof, one can probably verify that in finite arithmetic, if you assume that 2 to the n exists, then you can prove there's a prime number in the interval from n to 2n. But what if you just assume that 2n exists? There doesn't seem to be any room to do the sums you need to do to implement Erdős's proof. Looks like you need a new proof. All right, Ramsey's theorem. So I have to introduce some notation. Suppose n is a natural number. A set X is an n set if it has exactly n elements. For each set Y and for each natural number n, we'll let bracket y to the n be the collection of all n subsets of Y. It's not standard notation, but it's simple enough. So here's Ramsey's theorem. It says take any natural number n and take another natural number k bigger than n. Then there's a natural number m such that if you color the n sets from the numbers 1 up to m with n colors, that's the function pi, then there's a k set, all of whose n subsets are colored the same. So you have a coloring of the n sets from m objects. You specified a threshold k, and then you can find a k set of those objects, all of whose n sets are colored the same. This is a starting point for a whole area of combinatorics. Okay, there's the infinite version of Ramsey's theorem. Now we color the n sets of all integers. So if n is a natural number, we color the n sets of natural numbers with n colors. Then there's an infinite set of natural numbers, all of whose n sets are colored the same. Okay, so that's more elegant to state. Now, Ramsey's theorem is proved in arithmetic. There's a stronger version, which is proved in finite arithmetic, because you have to be more specific about the estimates. And the infinite Ramsey theorem, of course, makes no sense in arithmetic, because you don't have infinite sets of natural numbers. So it's a theorem of second-order arithmetic. So there's the Erdos-Party problem. So for every positive integer k, let's let e sub k, e for Erdos, be the least m bigger than k, such that if you color the two sets with two colors, you'll find a k set, all of whose two sets are colored the same. So why is this the party problem? Well, if you invite e sub k many guests to a party or a lecture, then you'll be guaranteed to find k many individuals who mutually have never met or mutually have met. So the coloring at did you meet or have you met or have you not met? Okay, so now you can drill down and then look at E5. So what's known? Well, it's bigger than or equal to 43, less than or equal to 48. What about E6? It's bigger than or equal to 102, less than or equal to 165. So what's Erdős' conjecture? It's within human capability to determine the value of E5. It is beyond human capability to determine the value of E6. So these are hard problems, possibly. Okay, so let's move on. Paris-Harrington theorem. Similar to the Ramsey theorem. So for every number n, there exists a natural number m. We color the n sets with n colors exactly as before. We find a set A, all of whose n sets are colored the same. Cardinality of A is bigger than n. So far, I'm just Ramsey. Now we're going to add one thing. That the cardinality of A is greater than or equal to its least element. Seems like an innocuous change. Now, this easily follows from the infinite Ramsey theorem. Good exercise. And what's the idea? Well, look, an infinite set has more elements than its least element. So if you use the infinite Ramsey theorem with exponent m plus 1, you can easily prove the Paris-Harrington theorem with exponent n. So what's the punchline? Theorem can't be proved in arithmetic unless arithmetic is inconsistent. So just change the Ramsey theorem a little bit, and you get something about the finite which the finite cannot prove. So this suggests we can define numbers now. So I'll call them the Paris-Harrington numbers. So for every n, let PHN, PH for Paris-Harrington, be the least witness for the Paris-Harrington theorem with exponent n. So it's the least m such that if you color the n sets from 1 up to m with n colors, you can find a set A, all of whose n sets are colored the same. It has, of course, more than n elements in it, otherwise it's not so interesting, and it has more elements than its least member. So what can we say about these numbers? pH 10 cannot be written in decimal notation in our universe. In fact, pH 5 can't be. These are numbers large beyond imagining. And necessarily so, or you'd be able to prove the Paris-Harrington theorem. The Paris-Harrington theorem is just a theorem that for every n, pH n exists. So these are much bigger than the usual large numbers you may have seen, like the Knuth numbers with the up arrow notation. These are just staggeringly large. Okay, so pH 10 can't be written in decimal notation in our universe. pH 11 is vastly bigger than pH 10. These numbers grow in enormous leaps and bounds. Okay, so now as a logician, we can do Gödel sentences. So there's a formula first. I have to set this up. There's a formula in finite arithmetic that I need to be able to talk about the Paris-Harrington numbers. So there's a formula in the language of finite arithmetic. It holds of x. It expresses that a pH x exists. So there exists a y such that y is equal to the xth Paris-Harrington number. And 2 to the 2 to the y exists. The reason for the 2 to the 2 to the y is to give ourselves enough room to verify that what we're claiming is the Paris-Harrington number is. So we have to be able to look at all the colorings. So 2 to the 2 to the y is overkill, but it's a security blanket. Okay, so now the Gödel sentence, theta g, it's in the language of finite arithmetic. It's a small length. You could write it down on one slide. It expresses that there's a proof of my negation, a formal proof, from finite arithmetic of length less than pH 10. Remember that impossibly large number. And pH 100 exists. So more precisely, that a phi sub pH of 100 holds. That's why we introduced the formula. So this is a standard Gödel-like sentence. It's the liar paradox. You know, this statement is false. The paradoxes all lead to interesting theorems. This is the interesting theorem, or the original Gödel proof was the interesting theorem you get from the liar paradox. There's a wrinkle here, though, in that there's a proof of the negation, but something really big exists. So the chaos isn't around the length of that proof. It's way, way far away. All right. Assume arithmetic now. Now, I should say, arithmetic does not prove that pH n exists for all n. But it does prove that pH 100 exists. It proves for each specific n that pH n exists. It just can't prove that for all n, pH n exists. And had I done my homework, so it's not too hard to write down a proof in arithmetic that pH 10 exists. But what about pH n, where n is pH 10? That can't be proved from arithmetic in any proof that can be written down in our universe. So how do we know that the Paris-Harrington numbers aren't a contradictory notion? So, more precise, so assume PA, there is a proof of not theta g from finite arithmetic of length less than pH 11. You just look at all the proofs of length less than or pH 10, and you just verify that none of them is a proof. But how can we be certain that there's no proof from FPFA of less than that enormous number, pH 10? All right, so let's look at this a little more. Maybe we shouldn't even care. So the real question is, how can we secure the finite? So In PA, we know there's no proof of the negation of theta g from FPFA of length less than theta, pH10, but that doesn't obviously imply there's no proof of length less than pH10. Well, if you work in finite arithmetic and you assume that pH 101 exists, which is that enormously large thing over pH 100, then you can show that there's no proof of not theta g from FPFA of length less than pH 10. But is that a convincing argument? If pH 100 is a contradictory notion in finite arithmetic, we're working from a false hypothesis, a contradictory hypothesis. Not helping. But how do we know we can't find by physical or mathematical means a proof of not theta g from finite arithmetic of length less than 10 to the 24th? Forget about length less than pH 10. Or that we can't find accessible, verifiable evidence which converts to a proof. We built not theta g from FPFA of length less than pH 10. We build some weird quantum machine, it flips a lot of coins, and voila, we find evidence that there's such a proof. Well, we have to care about this. Because a proof of length 10 to the 24, if we have it, we can see it. It's verifiable. So what would the consequence be? It's the end of days for mathematics. If there's a proof of not theta g from finite arithmetic of length less than 10 to the 24th, all of mathematics is wiped out. Because it says that pH 101 is a contradictory conception. So a number theory is dead. All of mathematics that rests on number theory is gone. You can't define this away. So how can we be sure? Now you might say, well, that's silly. I look at the world. Mathematics is successful in the world. But wait a minute. You can't use pH 50 in finite arithmetic to accelerate the proof. Otherwise, you'd have a contradiction. Because remember what the sentence says. The sentence says there's a proof of my negation of length less than pH 10, and pH 100 exists. So if I could work from the assumption that pH 50 exists and use all that rich structure which dwarfs the structure of the physical universe to show that this string doesn't exist, well, I've in fact shown it does. So the richness of FPFA in the context of pH 50 exists is far beyond anything you would need to do a model of the observable universe. So you can't use the regularity we see in the physical universe as evidence that this string doesn't exist. Something to think about. I'm not crazy, don't worry. Okay, so one way you could secure the finite would be to secure the infinite. If pH 100 is an inconsistent conception, well, then second-order number theory is, of course, an inconsistent conception, and that should be easier to see. So let's go further to see if things unravel. And if they don't, maybe that's evidence that we're okay. So I really want to emphasize that if that string, so I remember when I took my first analysis class, I remember the professor saying, yeah, you know, they might find a contradiction in these axioms, but we'll just define it away, like we defined away Russell's paradox. You're not going to do that here. There is no way to define away this contradiction. All right, so the simplest setting for the study of the infinite is second-order number theory. And we have the axioms. So can we answer the basic questions of second-order number theory using or starting from the formal axioms, and thereby show that the conception of arbitrary sets of numbers makes sense? Okay, so we're going to look at the very simple collections, the projective sets. Now, these are not the projective sets of algebraic geometry. So the standard structure we have the standard structure for second-order number theory, And that's really the structure of the real numbers in disguise. I should have put the integers in there as a predicate, and I didn't. So amazing how many times you can look at slides and still miss things. Together with a collection of, well, actually what I wrote is accurate. Together with a collection of simply defined sets of real numbers, the natural numbers are pretty simple. So these are the projective sets. How do we generate them? There are two equivalent ways to define the projective sets. The first way is the model theoretic way. You view the reals as a subset of the sets of all natural numbers. That's easy by Dedekind cuts, identifying the natural numbers with the rationals. And then you consider those sets of real numbers which can be logically defined in our structure for second-order number theory from parameters. Now, there's another way to do it, and that's the calculus, use calculus. So you look at all the sets of real numbers which can be generated from the initial set R of all real numbers in finitely many steps using two very simple operations. First operation is from a set, take its complement. And from the set, and the second operation is if you have a set, you're allowed to use a function from reals to reals, which is continuous if you restrict it to the space of all irrational numbers. And then you take the image of the set. So you can take a set, go to its complement. You can take a set, take one of these functions, which is a basic notion in calculus, and look at the image of the set. So it's important here that this is continuous when restricted to the space of all irrational numbers. That's slightly different than saying it's continuous at every irrational number, because we're restricting to the space rather than looking at the whole space. But what questions should we consider? We have our objects. Well, the natural choice is given by localizing two of the most famous questions of set theory, the axiom of choice and the continuum hypothesis. So let me just quickly do that. So we're going to localize the axiom of choice to this arena. We'll call that the projective axiom of choice. And here's the definition. So first of all, we can define projective subsets of the plane exactly the same way as we define projective subsets of the real line. So if we have a projective subset of the plane and we have a projective set X, let's suppose that for every real number R, there is a real number S such that Rs belongs to X. In other words, X intersects every vertical line. Okay, then there exists a projective set Y contained in X so that in every vertical line it picks one point. So what the axiom of choice would tell you there is such a set Y, but it wouldn't tell you that it's a projective set. So we're localizing the axiom of choice to the universe of projective sets. So that's a projective axiom of choice. It's not clear whether it should be true or not, but certainly an interesting question. What about the projective continuum hypothesis? We do the same thing. So remember, the continuum hypothesis is the assertion that if you have an infinite set of real numbers, you can either match it with the natural numbers, there's a bijection, or you can match it with all the real numbers by a bijection. So now it's clear how we would localize that. We just need the notion of a projective function. Well, that's obvious. Function is identify a function with its graph. Graph's a subset of the plane. We've already defined projective subsets of the plane. And so for projective sets of real numbers x, y, we have the notion of a projective function. Its function is graph is projective. And so now we can just state the continuum hypothesis. It says that if you have an infinite projective set of real numbers, then it's either projectively bijective with the natural numbers, or it's projectively bijective with all the real numbers. Again, we're just localizing to the projective sets. By 1925, so almost 100 years ago, these problems were considered hopeless. Lose in 1925. And there's a reason. They're both unsolvable. Both of the problems given by the projective axiom of choice and the projective continuum hypothesis are formally unsolvable from our axioms. In fact, they can't even be solved from the ZFC axioms. Something is seriously missing. Well, maybe all's not lost, and these questions can be answered by sharpening our conception of the structure given by all sets of natural numbers. We had our initial set of axioms. This tells us we're missing some axioms. We need to sharpen our conception. And maybe in doing that, we can answer these questions. And maybe in doing so, show that we're successful in studying the infinite, and maybe thereby secure the infinite. So one way we could do this is introduce a notion of a projective frame. A projective frame is an extension of the formal axioms of second-order number theory. It's supposed to provide a complete description, scare quotes. The extension should be specified by at most a recursive set of formal axioms. The extension should be immune to Cohen's method. More precisely, Cohen's method should not be able to be used to show that questions are unsolvable on the basis of the frame. Now, there is a projective frame given by Gödel's axiom for set theory. The axiom V is equal to L. We'll call that the Gödel frame. The Gödel frame implies the projective continuum hypothesis, and it implies the projective axiom of choice. Great. And it's a frame, so it's immune to Cohen's method. Good. But there are other projective frames. The projective frame given by the Michalski-Steinhaus axiom, the axiom of determinacy, we'll call this the PD frame, PD for projective determinacy. Determinacy asserts that certain infinite games are determined. They're winning strategies for one of the players. I'm not going to define it further. So the PD frame also implies a projective continuum hypothesis, and the PD frame implies a projective axiom of choice. Great. Looks like the Gödel frame. So, but we can strengthen the projective continuum hypothesis and introduce the strong projective continuum hypothesis. So this just says that if you have an infinite projective set and X is not countable, then it contains an uncountable closed set. So a big projective set contains a big, simple projective set. The closed sets are, in some sense, the simplest sets. But they're not equivalent statements. Now, there's also the projective well-ordering principle. It asserts that there's a projective well-ordering of the reals. In other words, there's a linear order on the reals, not the standard order, which is a well-ordering. Every subset has a least element. Okay? And you could restrict to projective. The projective well-ordering principle refutes the strong, first of all, it implies the projective axiom of choice, because you just choose the least element in each vertical line that hits your set. The projective well-ordering principle refutes the strong projective continuum hypothesis. That's a projective version of the theorem that if you have the axiom of choice, there is an uncountable set of real numbers that doesn't contain an uncountable closed set. You just projectify that proof. Okay, so let's go back to our two frames. If you assume the Gödel frame, then the projective well-ordering principle holds. And that's why the Gödel frame implies the projective axiom of choice. If you assume the PD frame, theorem of Martin-Davis, then the strong projective continuum hypothesis holds. So the projective well-ordering principle does not hold. So the PD frame is in conflict with the Gödel frame. They're incompatible. Okay, in fact, there's a bewildering array of divergent projective frames. Many other frames have been discovered. Cohen's method actually yields projective frames in which both the projective axiom of choice and the projective and the strong projective and the projective continuum hypothesis fail. But for 25 years, the PD frame was in essence the only frame known in which the projective axiom of choice held and the strong projective continuum hypothesis holds. And during that time, a conjecture emerged that the PD frame is implied by those consequences, that it's the only frame where you can have both the projective axiom of choice, as I defined it, and the strong projective continuum hypothesis. Well, that would be great, because that would enable us to pick a preferred frame. Remember, that's what we're trying to do. Unfortunately, a whole new class of projective frames was discovered. These are frames in which the strong projective continuum hypothesis holds, the PD frame is false, and by theorem of Steele, the projective axiom of choice holds. So that conjecture is false. So it looks like the attempt to understand second-order number theory is completely failing. We just have a huge array of incompatible possibilities. So to succeed, we need to somehow identify, well, now that is a typo, the one true projective frame among this ever-expanding collection of projective frames. So, well, we'll move to a different perspective, the V perspective. So the axiom that there is a measurable cardinal is a fundamental large cardinal axiom was first defined by Ulam in 1930. So a large cardinal axiom, that's going to be very much a theme tomorrow. These are axioms which assert the existence of really big sets. So big, you can't prove they exist. So Rowbotham in 1964 showed that if there's a measurable cardinal, the Gödel frame is false. Oh, so now we can cast out the Gödel frame. So the conception of V, the universe of sets, entails rejecting the Gödel frame. V is all about as many infinite sets as possible. It should be everything. So what about the other projective frames? So there was an unexpected and perfect alignment. So there's a Martin-Steele theorem in 1985. Assume there are infinitely many Woodin cardinals, then the PD frame holds. That's great. That suggests, especially for me, that suggests the PD frame is true. But the connection is even tighter. A few years later, I showed that the PD frame is actually equivalent to the theory of second-order number theory given by the ZFC axioms. Together with the axioms, there exists n many Woodin cardinals, one axiom for each n. So that's a perfect alignment. That's great. We've succeeded. But have we really? Well, first of all, now I'll be controversial. I'm not crazy. We now have a new truth of FPFA. The PD frame is consistent. Can't deduce that from the fact that ZFC is consistent. It's a genuinely new prediction of FPA, of finite arithmetic. How do you account for it? No one has been able to account for such predictions from the study of infinity, except for the conception of the universe of sets, where those axioms actually hold, or equivalent axioms do. So that's something to think about. Here's a truth, it's a mathematical truth, that the PD frame is not contradictory, but it's a truth you cannot prove. So the idea that all mathematics is we're all sitting around calculating isn't going to help. That's not it. It's not going to tell you, you're not going to prove the projective determinant is consistent. So it's truth beyond proof. Since I'm in a philosophy department, I kind of have to say these kinds of things. Oops, this is recorded. I want the last 3 minutes. Okay, so I'll make my usual controversial claim. I'm going to turn this into a prediction about the real world. My prediction is that this claim will not be falsified in this millennium, by any means. If we contact extraterrestrial civilizations in 100 years that have been working on this for 5 billion years, they won't have found the contradiction. How do you account for that? Now, at the end of this millennium, we're going to know whether my prediction is correct or not. Okay. But has this success secured the infinite? The PD frame is secured by the conception of V. But we're enlarging the scope of our investigation from second-order number theory to the structure of V. We're just kicking the can down the road. So to be consistent or fair, we should transition from considering projective frames to considering V frames. We went down the road of projective frames to try to solve problems that were unsolvable. We succeeded, but only by looking at a vastly larger structure, the universe of sets. So we really need to apply the same standards to that structure, or we're not being consistent. So is there an expansion of the ZFC axioms which yields a conception of the universe of sets, that's V, which is immune to Cohen's method? Cohen's method is the spoiler, and which is compatible with all large cardinals. This is the large cardinal test. So Gödel's axiom V is equal to L is immune to Cohen's method, but by Robotin's theorem, it doesn't pass the large cardinal test. So up to about 15 years ago, this seemed completely hopeless. And if I had been giving these lectures 20 years ago, and I would have given you 5 different reasons why there could be no such frame. There was a fundamental misunderstanding. Possible. So the ultimate frame. So by generalizing the, another misprint, projective sets to a vastly larger collection of sets of real numbers, one is naturally led to a generalization of the PD frame to a single new axiom. And that axiom is called V is ultimate L. And that's homage to Gödel's V equals L axiom. And this is an axiom for the universe of sets in addition to the ZFC axioms. The axiom settles the problem of the continuum hypothesis. We know that. It implies it's true. It implies PD. That's less interesting. The axiom yields a V frame. We can already prove that. So Cohen's method can't be used to show that statements are independent of this axiom. That's great. But is V equal to ultimate L the one true missing axiom we seek? Does V equals ultimate L even pass the large cardinal test? So let's go back to that. So Robotin's theorem was a successor of this theorem of Scott, that if you assume V is equal to L, there are no measurable cardinals. Now, Robotin's theorem was more subtle. Robotin's theorem was that if you had a measurable cardinal, the Gödel frame was false. So the difference between the two theorems is Scott's theorem is saying in L, there are no measurable cardinals. Robotin's theorem is a little more surprising, that if you have a measurable cardinal, there are real numbers that can't be in L. So the existence of big cardinals gives you new infinite sets of integers. So Gödel's axiom V is equal to L fails the large cardinal test in its first interesting instance, measurable cardinal. So again, because, okay, so now the ultimate L conjecture, which I won't state, is a precise mathematical conjecture which, if true, implies that the axiom V is ultimate L passes a large cardinal test. Now you may say, well, how can I make that claim? We don't even know what an abstract large cardinal axiom is. But it's quite convincing that this conjecture will show that V is ultimate L passes a large cardinal test. But we've been here before. Great. We have this conjecture. If it's true, maybe this is the true missing axiom. Maybe we can't solve the question. Maybe it's like the continuum hypothesis. Have we just traded one unsolvable problem for another? Well, the ultimate L conjecture, also if true, provides compelling evidence that the axiom V is ultimate L is true. And so is the missing axiom. So we're being teased with a possibility. One axiom does everything we want, pass a large cardinal test. All we have to do is prove this conjecture. And then we have to worry maybe it has no answer. And we're just back to square one. So the ultimate L conjecture, it turns out, is an existential statement of number theory. It must be true or false. It can't be meaningless. The ultimate L conjecture is not a conjecture about sets. It's a conjecture about numbers. It's a conjecture, one theory proves one sentence. That's an existential statement of number theory. Either true or false. If it's unsolvable, it's false. Because if the theory proves a sentence, we can see that it proves a sentence. So we haven't traded one unsolvable problem for another. Okay, why is it set theory at a crossroads? Now I'll make my controversial claim. If the ultimate L conjecture is false, that would arguably say that the whole methodology we've been using to understand these large cardinal axioms reaches a ceiling. And so we need a whole new method to understand the universe of sets. It will be back to square one. So we've got a 50, 60-year development of trying to understand large cardinals. It's all coming to a head now. We've got this one conjecture. We have the tools in hand to solve the conjecture. It's not like we have no idea what to do. It's also a level playing field. There are attacks to show the conjecture is false. So you could, cast your lot that the conjecture is true, develop the tools to try to prove it. There's a lot of partial results there. You could say, well, I don't think that's the way it goes. You could explore the other half. And there are plenty of ways that the ultimate L conjecture might be false. It really is a bimodal future. And every year, the two possibilities get further and further separated and sharpened. So this is going to get resolved. And if the ultimate L conjecture is true, in some sense, then the fun begins, because then we can fight about whether V is ultimate L. And if it's false, then we have to go back to the drawing board and start all over in trying to understand the universe of sets. Maybe we have to entertain the idea that we can't come to a sharp view of the universe of sets. But if that's true, then what about the consistency claims? There are some who say the continuum hypothesis has no answer. The universe of sets is inherently vague. But then, why is PD consistent? How could you say, well, I know nothing about CH, that's inherently vague, but way up there in the stratosphere, in the lofty peaks, I see Woodin cardinals. That doesn't make any sense, right? They say that big things exist and you can see them clearly and yet give up on small sets, to me, is an incoherent position. So the argument that Woodin cardinals, or pick your favorite large cardinal, super compact or whatever, are consistent because of their existence in the universe of sets demands that we be able to answer questions like the continuum hypothesis. And we should have a deeper understanding on why those axioms are consistent. The ultimate L conjecture gives perfect clarity at some level. It crystallizes out the universe of sets, and you can't use forcing. You can really start doing transfinite mathematics, and that's the problem in set theory right now. You can't really do, if every problem you want to look at is unsolvable, how do you develop a structure theory? All you can do is develop a theory of possibility. But that's not a structure theory about the universe of sets. And if you're hamstrung by unsolvability, there's no way to build a structure theory for the universe of sets. So the V equals ultimate L axiom offers the possibility of a genuine structure theory for the universe of sets. It's also the only axiom known that has a candidate for doing that. See, normally if you're in this situation, you can find surrogate axioms that do kind of what you, it's like an existence proof that the axiom might exist because here is one. It's like I'm looking for a unicorn. Well, over there's a horse with a little horn, so it's a pseudo-unicorn, so maybe unicorns exist. There's no known artificial axiom that is both passes a large cardinal test and is immune to Cohen's method and crystallizes out the universe of sets. So the V is ultimate L is really the only possibility right now. So if it goes down, because the ultimate L conjecture is false, our methodology hits a ceiling, it really is back to square one. Okay, that's it. Thank you.